This is what we're going to talk about. I'm not a guy who likes to read slides. I don't even like slides. So high level, we're going to talk about graph theory. That's going to be the main recurring thing that we talk about in this entire session. Past that, we'll talk a little about OSPF adjacencies, pretty minimal. Then we have optimal routing. We'll talk about a couple of OSPF optimizations there. Then we will do the forwarding address stuff, which is also pretty fun. And then we'll finish up with some automation, which is new from last year. For those who haven't signed up for the WebEx Teams chat, you can do this through the app on your phone. My good friend Mike Zig, he's holding his hand up. He'll be the one answering the questions that you put into the chat. You have two choices for asking questions. You can raise your hand and ask me, or you can type it in the chat. If you think it's maybe off topic or extremely detailed, then you can ask him, okay? So you have a couple choices there. I like to set expectations early on. Sometimes people come to a session on troubleshooting OSPF and you think that I'm going to do things like review TAC cases or talk about software versions or talk about line cards and other ridiculous stuff that has nothing to do with OSPF. Some people like that. I don't. We're going to focus on basics. And when I say basics, what I'm really talking about is understanding how OSPF works under the hood. Show of hands, who's comfortable in here troubleshooting any OSPF problem only looking at the database? So you have no access to OSPF neighbors, you have no access to OSPF interfaces or any of that. Who's comfortable only using those commands? Okay, like 3 people. So good. At the end of the session, hopefully the number is closer to 200. You're going to get a deep understanding of how that stuff works. I don't like tricks, I don't like gimmicks, I don't like shortcuts, because that doesn't make you a better engineer. That makes you a script kiddie. And that's not what this session's about. This is a 3,000 level session. This is advanced stuff. This is probably one of the most technical sessions you will attend at Cisco Live. And I'm not saying that to belittle my peer speakers. I'm just telling just the facts. We're going to do a lot of complex demos. That's why you have a topology in front of you. I'm trying to teach you things you're actually going to remember, useful skills for real life, not just random show commands. Here's what I'm not going to do. Don't try to stump the chump with me and ask me questions about RFCs and bits and codes and header lengths. I don't play that. I'm not going to answer your question. Ask it in the chat and I'll answer it later. I'm not up here to just throw my encyclopedic knowledge at you and see what sticks. I mean, who wants that? Not really. So that's what I'm not going to do. We're not going to look at every single possible OSPF problem. I'm going to zoom in on things that are complicated. I'm going to try to weave it into a larger story. That's why we have this big topology, and there's a lot of problems with it. If you have the PDF, if you see that little paper in the upper right corner, those are reference slides, and they will not be shown in here, but they are backup. And there's a lot of extra interesting stuff there for people who want to go and look at a couple different things. Okay, start off by talking about graph theory. So I'm talking high level here. In a graph, there are really only 2 components that matter. We've got edges and we've got vertices. A vertex is equivalent to like a router, and it has an ID associated with it. So in the context of OSPF, we're talking about a node with a router ID. An edge connects exactly 2 vertices. So in OSPF, it would connect exactly 2 routers. Now in your head, you might be thinking, well, how does that work on broadcast networks? We're going to cover that. I want everyone just to get a high-level appreciation for what this is. Don't think too much into it. This isn't a theoretical math class, and we're not going to do like proofs or nothing like that. I just want everyone to understand that when I talk about graph theory, this is what I'm talking about. Okay, I'm not talking about like XY coordinates and none of that. Okay. Now I also want to talk about the scientific method a little bit. This is like that stuff you learn in middle school, and you're like, yeah, whatever. But this is how we go through our whole troubleshooting methodology. Who's ever worked on a network? I mean, I think we've all done it. Maybe in our earlier days, is when there's a problem and we just throw every show command we can do and we trace route everything. Right? We're just throwing punches in the dark, hoping something connects, and none of it does. And that's just foolish, and we've all done it. We're going to take a very different approach here. We're going to spend 95% of our time thinking and reasoning through problems, and then we are going to, with precision, surgically correct the problems. Because why? I mean, who just wants to spam show run over and over again and try to find the bug? That's pretty lame. That's not what we're doing. So I'm not going to read this to you. I'm sure you've probably all read it by now. This is a process we're going to repeat many times. Okay, so The way I came up with the curriculum for this course is a year ago, I went on Twitter, which is super scientific, and I asked a simple question. You can all read it, but I had two hypotheses. Okay, so first step, I had to think something, and then I had to test those hypotheses. And this was my quick experiment, and I'll let you read the slide. Basically, I had a couple hypotheses, and I asked my question in such a way that the first and the last answer led me to my conclusion. So people need to understand, or they want to understand how the linked state database works in detail, and they also want to understand how to navigate poor designs. For all of you looking at your topology right now, it's pretty nasty, isn't it? That's what we're doing. Okay, people didn't really care about nerd knobs, adjacencies, and mismatch hello timers. I don't play that. Not in a 3,000 session. Okay, reference topology, who doesn't have one? If you're in the back and you don't have one, there's some extras on the table, and if they're not there, come see Mike. Okay, everyone's got it. If you're in this session, you probably understand the basics of OSPF. You should understand what's on the diagram. Okay, let's jump into a problem, because this is troubleshooting OSPF, and I'm already sick of PowerPoint. So here is our situation. I'll let you read it. So we're kind of zoomed in on the center of the diagram here. We got these 6 routers. We are trying to do a web download from R1 to R4, and it's not working. And we recently updated R14 and did some hardening on it, and it just doesn't work. And this is what we've been told. So let's use our scientific method here. Now I'm abbreviating the steps a little bit, but let's think about it. Why is it working? Or I should say, why is it not working? Or what can we observe from the current environment? As we're going to see shortly, our ping and trace route are going to look just fine. From R4 to R1, it's going to follow through R2 like we expected it would. Then we have to ask the question, why are they failing when ping and trace route work? Some of you may have a hypothesis already. Maybe it's the same as mine. Maybe we think that R1, there's some kind of asymmetric routing where R1 is preferring a path through R14. Does anyone think that might be the possible cause? Especially after we did some security updates on R14? Okay, oops. Sometimes I lose track of where I am. So here's what we're going to do now. Can you guys see that okay in the back? I tried to increase the font a little bit from last time. If you can't see, there's some seats up here. So the way we're going to solve this is I'm logged into R4. That's a router in area 0. And what we're going to do is from R4, we are going to draw the topology from the lowest level of all these area 0 routers, okay? So I'm not going to do any look at the neighbors, look at the IPs, or none of that, okay? So let's just start off confirming our suspicions that ping and trace route work just fine. I can get to R1, and it routes through R2. So if you just look at the last octet of these IPs, that's the router number. So I just keep it easy so we don't have to talk about IPs all day. All right, so for those who want to follow along, you can turn over your topology, get a pen out. If you want to draw this with me, I'll tell you up front that if you're not as comfortable with OSPF and you've never ever done this before, you may just not want to participate and just pay attention here. Otherwise, you're going to be like this and you're going to get mad. So what we're going to do, the goal of this is pretend like you don't have the diagram in front of you and you're dropped into this router and you're told to troubleshoot a problem and you don't have access to any device other than this. And we're going to make it even harder by not giving you access to any commands other than the detailed database show commands. Now, I'm not just doing this as some stupid parlor trick, because that's not what this is. I've used this in real life to solve a number of different problems. The point is that we need to understand how OSPF works behind the scenes. So, show IP OSPF, and what I'm going to do, because I like to be as specific as possible, I'm going to specify the process ID, which is 1 all day, and I'm also going to specify the area ID whenever it makes sense. And the way you do that is like this. So I'm in process ID 1, area 0. Okay, so these, first couple, you're going to see me type this a lot. So, I'm going to blaze through it often through this class. So in process 1, area 0, I want to examine the database, and I want to look at the router LSAs. If you're in this class, you should know what a router LSA is. Does anyone not know? I can do. So long story short, a router LSA represents the individual nodes in the graph. So we should have 6 at this point. Ignore the virtual link for now. That's broken. We got to fix it. But there's 6 right now. So we're going to start off by looking at R4. There's 2 ways we can do that. We can use the keyword self-originate, which is quick and easy, or we can specify the router ID, which is 10.0.0.4. So we're on R4, and we're saying, what is the LSA1 that was generated for R4? And here are the details for it. Okay, I blew past the header because I don't really care a whole lot about it, and we'll look at that later. But here are the guts of it. The way you interpret this is it's a list of link types, or links. You can look at it that way. So OSPF is a link state protocol. This is what we mean by links. These individual components are pieces of the topology. Now, I'm not going to go through line by line all day, but I'll do it a little bit slow on this first one. So just by looking at this at a high level, we can see 5 kind of paragraphs here. And the first line of each paragraph tells you what kind of link it is. In this case, we only have 2. There's a stub network, and there's another router, which is a point-to-point link. A stub network is just an IP subnet. So for example, if I had 10 VLANs hanging off the back of me, I'd have 10 of these stub networks. And you can see that the information contained within it includes the IP address, the subnet mask, and a cost of 1. So that top one, as you can probably guess, is a loopback. 10.0.0.4/32, cost 1. The other stub networks are the transit links, which are all /24. Those are just the links between the nodes. I could have suppressed them. I didn't really want to here. But the more interesting ones are the connections to another router. You can see the neighboring router IDs are displayed there. So from R4's perspective, I have links to R2. Well, let's look at this. I have a link to R2 and I have a link to R5. Is that consistent with what the diagram says? It should be. It's not. No? R4 does? Yeah, it does. Sure it does. Somebody was shaking their head. I was like, oh man, did I screw this up already? So yeah. So now that we've discovered that, what we can do is we can go back to our picture, and if you're drawing it, what you might end up is something like that. Now I'm going to use green to show new additions, because as we go, there's going to be multiple slides here as we build this out. What I would have is something like this. On the top right, I've got that box. You might have seen that there were 5 links total. I'm using the thick green arrows to indicate point-to-point links, so I'm connected from R4 to R2 and from R4 to R5. And you can see that this makes up almost like a piece of the diagram, and we're slowly building the diagram as if we didn't have it. Then off to the top right, I've got the stub networks. Again, I'm just enumerating them as subnets. Some of you may not be able to read that. It's not that big of a deal. I don't want you to focus too much on the stub networks. The whole point of this exercise is to redraw the diagram without having it. Who's ever seen a network diagram that was incorrect? Okay. Hopefully there's my value prop. So, okay, so let's continue. So we can go to R2 or R5 next. It really doesn't matter. I'm going to go to R5. So I'm going to be lazy and do a little up arrow here. And if I want to look at R5, I just put the router ID in there, hit enter, and I've got 5 more links here. So I'm just going to kind of scroll down so we can see all of it at once. So now this is from R5's perspective. Notice I'm still logged into R4. I only have access to R4, but now I'm looking at the network from R5's perspective. R5 has a number of different stub networks. It's got 3. It's got its loopback at the top. It's got some transit networks on the 3rd and 5th paragraph. But then we can see the 2 point-to-point connections. One of them goes to router 3. One of them goes to router 4. You can see that based on the neighboring router ID. Now, in real life, you may not have IP addresses that are this easy, but there's no reason for me to confuse you with IP addressing. That's just a waste of everyone's time, so I picked some easy ones. Again, it should be consistent with the diagram, right? R5 is connected to R3 and R4 on point-to-point links, is it not? So what we can do, again, is go back to the diagram and add to it. So I advanced to a new node. It doesn't matter. I just picked R5 here. And now you can see how this graph is being formed. Notice that when I draw my arrows on that right, it's a bidirectional graph. Just like in OSPF, we all know that the OSPF cost, for example, can be set different on the end of the same link, right? That's why the graph looks this way, is R4 has a connection to R5, and R5 has a connection to R4. The cost could be different, which is why we reflect it in this way. Does everyone understand the general process that we're following? I acknowledge that many of you may have never done it this way before, and you may not master the commands, and you may not be able to do it as quickly. I just want to get consensus that people can see how this is ultimately going to end up looking like our diagram if we didn't have it. That's what this is about. So I'm going to hide the slides for a while, and we're going to build the rest of this without looking at it. So if you followed along so far, then feel free to keep drawing because we're going to go through it. And then at the end, we'll quickly make our way through the slides. So okay, so what have we done? We've done 4 and 5. We'll do 3 next. I think that's the order I did. So this one's only got 4, but something's different here. Who can see something different? There's something new. There's new information. Yeah, there's a transit network. What's that? What's it represent? Why is it different? And if you need a hint, look at the diagram and see what's different. What does R3 have that the other ones don't so far? No, the tunnels are in area 2. It has a multi-access network. So the other, I did point-to-point links on the other ones, and this is a broadcast network, so it's a little bit different. So we've got our connection back to R5, which we know. We got a couple stub networks, those are boring, but then we have this transit network. You can see there it says designated router address. So we're dealing with the DR here, so okay, cool, that's interesting. You can see here in this case that the DR address and the router interface IP are the same. That is one way of determining who the designated router is. It's R3, just based on this. Because if I looked at R3 and its address is 1.3 and the DR is 1.3, that means 3 is acting as the DR here. So there's a few ways we can go about this. We could go and continue, we could go back to R5 and we can continue on to R2 because we learned about that earlier, or we could move on to this transit network. Now, the difference here is that we've been looking at router LSAs so far. We've been looking at the LSA type 1 and the specific information contained within it. I like the designated router, which is the LSA type 2. It's called the network LSA. And the reason I like it is because it's real easy. It's literally just a list of connected routers on the multi-access network, and it contains a little bit of extra information. So let's break that open real quick. Now the command we use for that is our regular show command for the database, and then we use the network keyword followed by the designated router IP address. So this one's real basic. There are 3 routers connected on that network, are there not? 1, 2, and 3. Clearly identified there. It also provides the network mask as /24, because that is going to be consistent on a broadcast network. So now if you're drawing this, now we've learned about a connection from the DR to R2, and we've also learned about a connection to this new router called R1. So now that we have this information, we can continue a few different ways. We can go to R1, we can go to R2. Maybe, I think it would be useful for a second to go back to the slides real quick, just to get caught up. So here's kind of where we left off. We just checked out R3. We checked out R3, and we learned this new connection to a designated router. So I've got a little dotted rectangle for it, because this is what's known as a pseudonode. Some people like to call it that. For those of you who don't understand why we need that, part of the reason I talk about graph theory early is I like to stress the point that when you're talking about graphs, an edge connects exactly 2 vertices. So when you're on a multi-access network with potentially more than 2 routers, you need to have a point of virtual aggregation. Now, I'm not talking about like route summarization or hub spokes, nothing like that. This is just to make the graph complete, and the DR serves as that point where everyone forms a topological session, or neighbor, if you will, with the designated router. And that is how the topology gets built. We're going to actually break this later on. We're going to see what happens if you screw this up. The other thing I want to point out is that the costs from the DR are 0. Think about that. If I have 2 routers and it's an Ethernet interface and I leave it as a default broadcast network and I plug them in together and they both have a cost of 10, the DR doesn't add any extra cost. It's just part of the graph. It's one of the only places in OSPF that a cost of 0 can be used. So at this point, we've looked at the DR, and now we have a choice. We can go to R1 or R2. Now, if we wanted to finish this quickly, we would go to R1 because we all kind of hypothesized that's where our problem was. And if we were solving this in real life, we probably wouldn't draw the whole network like this. We'd probably go straight to R1. But that's not fun, so we're going to go to R2 instead. So let's check out R2. R2's got 6 links, so we're going to have to scroll a little bit here. That top one is the loopback. It's just a stub network, so I'm going to scroll past it because it's not interesting. These other ones, we've got a couple different connections here. So there's 2 more stub networks. Again, these are just IP subnets. We're not too interested in those. But the 1st, the 3rd, and the 5th are network connections. So the first one is a connection to R4. We knew that. So that's just kind of the back connection to R4, which is where we came from. And it also has a connection to this new router called R14. That makes sense. That's in the diagram. And then we also have a connection to the designated router. Now again, you can see router 2's interface address is different than the DR's address. That clearly means that R2 is not acting as the DR in this case. So we've learned about R2, and we've now uncovered this new router called R14. So let's examine R14 and see how is it connected to the network, and it's got 5 links. Again, you can see how this gets old real quick after you've done it a million times, but the whole idea is that once it gets old and boring, you win. You get it. It's supposed to be old and boring. If you find it difficult, then keep going until it gets boring. It should be second nature. So at this point, we've learned about Connections to, looks like R2 and R1 from R14's perspective. Again, if you're looking at your diagram, this should all be consistent with what the diagram looks like, and we should be able to draw this out on our own. Granted, it's probably going to look kind of sloppy, but we would at least get all the links correct, all the costs, all the subnet masks. Now, if we were going to go through this in extreme detail, it would take the whole 2 hours. So what I'm trying to focus on is the links between the nodes, not all the individual subnets. So last but not least, we have to address R1. And I'm just going to leave this up for a second. Based on this output, who thinks they see the problem? If you need to look at the topology, go back and look at the topology. But ideally, you want to just take, yeah, so you were here last year. Who wasn't here last year that sees the problem? What do you think? Which one? Why is that a problem? Well, why is that bad? Why is metric 100 bad? It's just a number. What's the problem? Why would it cause an issue in the network? I'm giving you a hard time. I'm just trying to challenge you to elaborate. Anyone want to help him? What do you think, man? Yeah. So which way is R1 going? Which way do you think? Yeah. So just like we hypothesized, we kind of proved it true at this point. So imagine that you only controlled the R4 router and you work in a bureaucratic environment where no one else lets you touch their devices, power struggle type thing, right? We've all worked with silos and turf wars. So they won't let you log into R1. So you have to know exactly what the problem is. Well, you can tell them, hey, on that specific network, the interface that you have is 10.0.0.1. Whatever interface that is, your cost is 100, and that's wrong. And they're like, how did you know that? Be like, what's up? That's what I'm saying. And I've used it in exactly that case on a network that was in Brunei because they wouldn't give me access, and I was like, yeah, here's the problem. So it was cool. That was like 5 years ago, and I was like, I need to do a session on this way in the future. So anyway, that was that is the problem. So what we'll do now is we'll cheat and we'll just give ourselves access real quick, and I'm going to correct it. I just happen to know it's interface Ethernet 01. If I didn't, I could just do this command, and I could see that second line down. So here I go. I'm going to change it to 10. And let's go back to R4. We'll run that command again. Cost has been updated to 10. So you see no gimmicks here. Now we can also check our web download now, and it works. So if I failed to do the web download in the beginning, this would have timed out and not worked. So maybe I forgot to do that. So I apologize if I did, but this would have failed before. Actually, you know what? I'm going to break it again because this is not fun. If I like tell you, oh, you can trust me, it was broken. None of you believe me, so I'm just gonna wait. Trust me. I'm not getting. Yeah, see there. Yeah, see. Yeah, see. Yeah, see now it's broke. I'll do it again because I'm two out of 3. So it's obviously broken. So if we go back, I need to keep it fixed. So we'll fix it again. We'll give it a second, and it'll work again. So. Any questions so far? So the reason we did this, and I'm gonna summarize here in a second. There, okay, it works. So let's go back to the slides. And actually, before I do the question thing, let's finish just going through this real quick. So we already went through this, and I used the slides as just to provide an additional quick review of what we did. So you're gonna see a little bit of duplication as we go through. Hopefully that'll help other people learn. Some people like to learn this way. So when we checked out R2, there were 6 links. A couple, looks like a transit network, 2 point-to-point links, and 3 stub networks. R14 was connected like that, and then R1 was connected this way. And you can see there's that 100 right there. And if we make everything black and highlight the problem, I'd made it in red so it stands out. This looks just like our diagram. It's just more detailed. That's the power of this technique. So here's what we did. So conduct the experiment. So again, we don't know that changing that metric would work. That was just what we thought. We tested it, we changed it, we verified that it fixed the problem. We confirmed our hypothesis was true. So now we're done. We analyzed the result, clearly it worked. And here's the takeaway, and maybe some of you have already connected this in your mind. We used one command on one device and drew the whole network and solved the problem that was far away. I think that's cool. And that's what the main takeaway I want you all to understand. Even if you don't understand exactly every step what we did, and even if you need to remediate these things, and I suggest that you do, this is what I want you to really take away. I mean, yeah, I used a couple different IPs I plugged in there for different nodes, but all I did was dig around the database specifically what I needed to do, and methodically drew out the network. I didn't jump in, I didn't log into 1,000 devices and spam OSPF neighbors and then look at my diagram and then send emails and complain, right? That's how we do troubleshooting today, but that's not how I operate. But that's one way to do it, okay? So let's continue. Let's talk about repairing adjacencies a little bit. So so I think most of us have done troubleshooting on OSPF neighbors not coming up or there being problems at some point. There's like 20 different things that can go wrong here. Who wants to go through 20 OSPF neighbor troubleshooting statements for the next 17 hours? Yeah. So we're not doing that. We are going to focus on one particularly ugly issue that we can use the technique we just learned to help us solve. So you can see at the top it says issue number 3. If you're looking at the PDF, there was a whole bunch more issues. So each one of those links in area 1 has like 3 or 4 issues or problems with it. In this particular demo, they're all magically fixed, and one of them is broken, and that's the one we're going to fix here. The reason I did that is so that when you go back home next week after you sober up and you want to play with this technology and go through it, I've given you like 20 different trouble tickets you can troubleshoot, and the slides kind of walk you through it. So that's something you can do on your own time. I think you'll enjoy it. I want to focus on the hardest one. So if you can't read that, don't worry, we're going to get into it. But long story short is, hey, maybe one of our junior engineers sent us this output. He's like, hey, I got this mismatched network type. Okay, we know that's going to be a problem, but why is it going to be a problem? Be specific in your explanation. Now, don't shout it, but just think about in your head. If you were trying to explain to someone, he's like, hey, Joe, I got this problem. I got network type broadcast and point-to-point. And if your answer is, well, the Cisco docs say you can't do that, wrong. You need to have a better answer than that. So I'm going to teach you what that better answer is. So I'm going to hypothesize that there's a problem with our graph here. One side's trying to do this transit network, the other side's trying to do point-to-point. So what's going on? All right, that was on R10 and 11. So let's just, again, junior guy goes in there, he does his OSPF neighbors. He's like, oh yeah, that second entry, it says, I've got a neighbor from R10, which I'm sitting on. I've got a full neighbor to R11. That's great, it works. I'm good. Neighbors are up. Ticket closed, right? Nope, not really. And if we look at R11, we're going to see the same thing. So let's draw part of the Area 1 graph. Now, I'm not going to draw the entire graph for Area 1. I think that's just, excuse me, it's a little bit repetitive, and I would rather spend time focusing on the issue here. So clearly, we could draw all of it, and I'm going to show you a reference diagram that you can use to check your work. But let's just start on R10, and we'll say show IP OSPF, process 1, Area 1. Remember, we're in Area 1 now. Database. And I want to start on R10, so I can say router self-originate. So I'm saying I want to look at my local LSA1. How am I connected? How am I configured? So I've got 3 links. I've got my stub network, which is my loopback address, my /32, not that interesting. Then I've got 2 transit networks. The middle one is the transit network between 10 and 11. Again, if you look at the second and third octets, I try to make it easy. And the bottom one is a transit network between 2 and 10. Maybe you didn't expect to see a DR between 2 and 10, and maybe you think it's unnecessary, and you're probably right. But don't be distracted by it. It's not relevant. So if you were drawing this, you would draw R10, and you draw a connection to a DR. Now, at this point, the next step that we need to do is we need to ask the DR, which is 10.10.11.10, who are you connected to? So we can go up here. We can say, I want to look at the network LSA of this. And as we would expect, R10 and R11 are connected. Now, up to this point, if we didn't already know there was a problem, this isn't indicative of an issue. Like if someone didn't call us and say it's broken, please troubleshoot, at this point, this could be perfectly fine. Assuming that R11 was actually configured as a broadcast network, but we just happen to know that it's not. So we really haven't uncovered any problems yet. Now, before I do this command, before we dig into R11, can anyone guess what we're going to see on R11? Are we going to see a transit network connection to the DR, or are we going to see something else? Yeah, somebody said probably point-to-point. That's right. So what we're going to see is R11 has a point-to-point network to R10, that third entry down. Now, this doesn't really make sense, because from a graph perspective, one of them is connected to the transit route, the DR basically, and the other one is connected on a point-to-point link excuse me, and that just makes the entire topology not work. So what I'm going to do is I'm going to show you kind of what that looks like, because it's a little bit hard to draw and it's a little bit hard to think about. You don't have to worry about the outputs. Again, those are kind of for reference. We just looked at them live. But if you focus on that picture, I've tried to highlight the problem with those red lines. The first two things we did down at the bottom, it's all black because there was no problem with it. We started at router 10. We had a connection to the DR. That's cool, no problem. And then we had the DR said it was connected to R11, but R11 said it was connected directly to R10. So don't mistake this for being like an asymmetric routing thing. That's not what this is. That's not what I'm drawing. What I'm drawing here is a completely invalid OSPF topology, and this will not work. You won't be able to pass routes. You won't be able to pass traffic. The link is broken. So in order to fix that, I'm just going to show IP OSPF interface brief. Again, I don't like using these commands, but I just want to demonstrate that I do, in fact, have a broadcast network type, and I'm not sharing. Thank you. Good thing I didn't do much. All I did was this one command, and you can see the third entry down. So it says DR there. That means I'm using a broadcast style of network. So I'm going to fix that real quick, if I could type. And we're going to see everything get refreshed. And if we do a quick, we just kind of up arrow here. If we look at our self-origination now, that might need to get refreshed. Let's give it a second. There. So you can see that second entry, I've got another router link to R11. And this transit network at the bottom was the connection to R2, and that hasn't really changed. And at this point, we can say show IP route to 11. We can see it's an intra-area route. It's connected on the link, Ethernet 03 between the two, and if we trace route, it should just be a single hop away. So we fixed it. This was kind of an interesting issue because the neighbor was up. We didn't get some obvious message about hello timers mismatched or authentication key was wrong, like whatever. I don't want to talk about that. So that is why I thought that was an interesting issue. Now, here are a list of other problems that could happen. I've highlighted in blue the issue we just looked at. And if you go through the PDF on your own time and you want to play with this, these are the issues you're going to see on each link. And the workbook will kind of walk you through that. But I wanted to highlight that one issue because it fits into our narrative about understanding how OSPF works behind the scenes without getting into the memorization about all these little settings that you can put into a search engine and get the answer to in about 13 seconds. Okay, so that's all we're going to talk about adjacencies. Any questions? Yes?
If you turn on terminal monitor, might you see logs telling you that you have a difference between your point-to-point and broadcast?
Yes. Yep. I didn't want to bring that up because even though that does help you, that's a relatively new message. I say relatively like past 5 years. Didn't used to do that. Logging can be helpful if you see it, but I'm pretty sure we've all missed logs in our lives, and we all know that the NOC never looks at the logs anyway. So sometimes it can be hard to do that. They just open a ticket and yell at you. But you're absolutely right. Not trying to take away with what you said, but you can get hints about what these issues are. But again, what you don't want to do is say, oh, I have a network type mismatch. Let me just blindly fix it and move on. You want to understand why it's broken. Yes?
Just as another part of this, somebody could have said, there's a logging level parameter set in the device that somebody could have set it to log level 3, in which case, this network type mismatch wouldn't show up in the log because you told the box to log.
Right, yeah, and it could be anything from configuration to not seeing the logs to running old code, but I'm not trying to say make your life harder on purpose. If you see logs or you can get by with the more basic commands, absolutely do it. Like, don't immediately rush to solve it the hardest possible way. But I guarantee at some point you will encounter problems that will require these advanced solutions. So you just want to keep that in mind. Thank you. Virtual links. There's nothing really fun about them. I don't know where I came up with this title. So what we're going to do is, I have a pretty ugly virtual link scenario. And it's ugly for a couple reasons. And some of those reasons are just the way the Cisco parser is built. So a couple different use cases for virtual links from a design perspective. We can use it, obviously. I'm sure we're all familiar with repairing a disparate Area 0 islands. We can also use it, even if Area 0 is contiguous, we can use it as a traffic engineering technique, maybe to send traffic between two Area 0 islands across another area, instead of taking a long path across Area 0 another way. kind of an awkward technique, but it does work. You can also create new ABRs. If you've got area 0, then area 1, then area 2, you can do it there too. Again, we're not going to get too much into that. I just wanted to make sure everyone's kind of tracking what the different use cases are. And now our virtual link is down. Now, without even logging in, I don't know how many of you have read the little footnotes, but I'll just tell you right now that the red lightning bolt serial links have a cost of 32768. The maximum cost for OSPF is that number times 2 minus 1. So if you look at your topology, the path from R4 to R11 is suspect. We'll leave it at that. So our virtual link is down. Some of you may understand why that is, but we're going to go and explore that now. See if we can troubleshoot this. So, all right, we're on R11, that's fine. Show IP OSPF1 virtual links. First line, virtual link to router 4 is down. Does anyone notice anything suspicious about the output? Yeah, the cost. Cost is a really big number. That number, 65535, is the maximum number, the maximum cost that any individual link in OSPF can be. But that number is valid, though. Like, if that were the actual cost, everything should be working. But it appears not to be. How can we figure out what the actual cost is between R11 and R4? Well, I mean, yeah, we could do show IP OSPF interface brief, and that tells us the cost on this interface, yeah. But without logging into every single device in the path, how else can we do it? Yeah, we can do what we just did. I want to teach you a shortcut. Now, I told you earlier, I'm not into gimmicks. I'm not into that kind of stuff. But there is one command I think a lot of people just don't understand how to interpret. Who uses the show IP OSPF border routers command regularly? And who's comfortable using it? Yeah, not too many people. The reason I like this command is it summarizes a lot of that database information for you, but it can be tricky to learn if you don't understand it. So we could go and we could trace the path, and it wouldn't take us that long to do. But we have another approach where we can say show IP OSPF border routers, and it's going to display this table of all these border routers here. And if we look at this, we can see the second entry. It says ICR4 as a border router. It's an ABR and an ASBR. We don't really care about that right now. It's reachable through area 1, and my cost to reach it is that number. That's inconsistent with the number at the top that says 65535. How do we reconcile these contradictory facts? Which one's right? Which one do you think is right? Top one or the bottom one? Yeah, the bottom one. This is telling you the actual cost between two nodes in the topology, and if we were trying to do it our way, we could have manually figured that out. The reason it says 65535 at the top is just an aesthetic thing. And Cisco makes it really hard to troubleshoot when they do that, because that's not the actual cost. So if you see 65535, it's not necessarily a problem, because we all know 65535 exactly would work, but you should be suspicious. So clearly in this case, it's too much. So why don't we try to fix it by, I don't know, let's go on R19. We'll go to his serial 11, the OSPF cost, 32767. So if I reduce his cost by 1, and I go back to R4, and I look at the virtual links from his perspective, oh, it's up now. We fixed it, right? Did we actually fix it, or did we only confuse ourselves further? This is one of the worst things about virtual links. Not only is the cost a lie, but the word up is also a lie. There are actually 3 states for OSPF virtual links. There's down, there's up, and there's actually working. So we are not in the actually working state. Can anyone hypothesize why that is? So I changed the cost on one side of the link. Like, yeah, how about I do the other side? So I did R19 to R11. So if I go to, well, here's how we can test it. So from R4's perspective, if I want to look at from R4 to R11, my cost is 65535. So the word up, all that means is from me to the other virtual link endpoint, my cost is 65535 or less. It means Up means my cost is okay. It means cost isn't the problem. So if you see up, don't troubleshoot cost. It's not the issue. Something else is wrong. But if we go to R11 and we try that same approach, that number hasn't changed. That word still says down. So we can conclude that there's a cost problem from R11's perspective. So what I'm doing is that horizontal serial link from R11 to R19 is what I'm modifying here. So now when we change that, everything should come up here shortly. If we look at yep, there it is. So the difference, this time, of course, our log message is handy. We get an actual neighbor, but the difference in the output is you see at the bottom, we have all these new lines. We have all this, basically looks like the details of the OSPF neighbor, adjacency state full, all that. This is the actually working state. Virtual link says up, there's not a cost problem, and everything is up. But look at that cost, that number hasn't changed, because we only reduced our cost by 1. So you need to be very careful when you're troubleshooting, because it lies to you in these little ways that can make it very difficult. And I've seen a lot of people on like the Cisco support forums that say, one side's up and one side's not, and I think it's a firewall, right? Why wouldn't it be the firewall? There's, like that kind of stuff. And I was like, you're missing some, again, this is fundamental knowledge. This is basic OSPF from 20 years ago. But I think just in our daily work, sometimes we overlook how OSPF is actually working. So now we'll just quickly backtrack through the slides for people who want to see those. So when we did this initial show commands, we saw down on both sides. That cost is valid, so we basically got lied to. Once we looked at our border routers on both sides, we saw that actually the cost is greater than 65535, and it doesn't completely work. So it's a cosmetic issue. You need to just be aware of it, and if you see that number, you shouldn't be like, aha, I found the problem. You should just be suspicious, and you should investigate it. Because if you see 65535 and the word up, you know it's not a cost problem. Now, there's a million ways Cisco could have done this better. We all agree on that. I'm just showing you how to do it. If we were to draw the whole graph for Area 1, this is what we would end up with. And you can see I've highlighted those high costs in red. And they sum to a number greater than the maximum cost for OSPF. The VL is up, but not really. We talked about that. This is that middle transient state where it's not actually working. The word up only means that your cost to the remote endpoint is functional. When we change the cost on the other side, we see all the adjacency state information, and everything is working properly. If we were to draw our new graph, and we were going to go through this manually, again, this is just the difference. It'll show the difference in cost there being reduced by 1, and now the sum of those two numbers fits into a 16-bit unsigned number, which is what OSPF uses for each of its links. The reason this matters is because the virtual link is actually part of the graph. So the virtual link is a link in area 0, is it not? And if it's a link in area 0, that means that our router 4 type 1 LSA should now have a 6th link, because they had 5 before, and we just added one. And when we look at it, we should expect the cost to be 65535. We should expect the remote endpoint to be router 11. And if we were to draw that out, and we're actually going to do this here in a second just to kind of solidify this, if we were going to draw that out, we would have this new, if we were going to update our diagram basically, we would have to add these new nodes, R11, R9, and R10, which are that triangle at the top of the diagram. Obviously, by fixing the virtual link, we expanded area 0, and that's what this is showing. So let me just quickly show that in case anyone is just wanting to see what happened there. So if I do, now that you see on R4 we got our log, show IP, OSPF, process 1, area 0, database, router, self-originate. Number of links, 6, about towards the bottom there. And we see this, I'll just stop right there. That first one's our virtual link. We've seen 4 different link types today. We've seen stub networks, we've seen transit networks, we've seen point-to-point links, and we've seen virtual links. There's only 4, and now you've seen all of them. So now you've seen all the different possible things you could see within a router LSA. And we can see that the cost here is showing 65535, which is valid, and the remote endpoint is R11. That's a new router, so let's explore it. If we look at R11, it's got its virtual link connection back to R4. It's got a point-to-point connection to R11. or sorry, to R9, I'm sorry, that middle one from 11 to 9, which is at the top of the triangle. And it also has that stub network, which is the transit link between 9 and 11. Now that we've discovered R9, let's see what R9 has to say. So he's got 5 links, again, not super interesting. 2 point-to-point links to R10 and R11. 2 transit networks that represent each one of those transit links, the IP subnets, and a loopback. Last, we have R10. Now remember, we saw R10 earlier from Area 1's perspective, but now we're looking at it from the Area 0 perspective, which was recently added. It's only got 2 networks, the point-to-point network and the associated IP subnet. So now we've drawn all, 9 routers in Area 0 or something like that. So we've finished all that. Let's test some flows now. So at this point, we need to, this is the really fun part. So we troubleshot bringing up the virtual link. Now let's see how the traffic works. If we send traffic from R9 down to R5, just looking at the way the topology is built, we have an Area 0 connection on the right side of the topology, but we don't have a virtual link from R2 to R10, for example. But when I do this trace route, which I'm going to show you next, when I do this trace route from R9, we can see the path is from 11 to 10 to 2 to 4 to 5. And if you look at your topology, it makes kind of a big C around the left side of the network. How is that even possible? There's not even an Area 0 connection between R2 and R4. Or sorry, between R10 and R4, or whatever it is. There's nothing over there. The virtual link is on the other side of the network. Does anyone know what this feature is called?
Capability transit.
Yeah. Anyone else know what it's called? This is the Area Capability Transit feature. It's very complex, and it's actually difficult to deploy. That's why I built the topology the way I did. So if we go to R11, the real question here is, how does R11 choose to get to R5? So remember, if you look at where R11 is in the network, it's in Area 0 and Area 1. And it says that it has an intra-area route to R5, which is true, because they're both in Area 0, right? But look at the next hop. It says R10. So R11 is claiming I have an intra-area route to R5's loopback through an Area 1 router. Like, okay. This is how the transit capability works. Because R11 has this extra insight into both areas, it can say, I have a shorter path to get to the destination without following the path that the virtual link was built. And the way that you can see that this is enabled, I mean, yeah, you can do the regular like show IP OSPF command, and it'll show up somewhere in there. I'm not sure I even care to look for it right now, to be honest. Oh, there it is. It says number of areas, transit capable is 1. Again, that's kind of a lame way to do it. The way I'm going to do it is looking at the border routers, and let's just look at R4. So from R11's perspective, when we look at our border routers, again, this helps summarize those complex decisions for us. And it tells us that we have a couple paths to R4. Through Area 0, we have a cost of 30 through Ethernet 03, which is the link between R11 and R10. And you see the word transit on the far right. We all agree that that link is not in Area 0. But it's reported that way because, again, R11 has that ability to take that shorter path. Just below that, it also has the ability to get to R4 the long way over the 2 serial links. That's why R11 is going to prefer taking that shortcut when it can. Let's turn, yeah, go ahead.
So this sounds like it's how Cisco overrides the classic problem of I have 2 areas, a link between 2 routers, and the link can either be in Area 0 or Area 1, and all kinds of, and what pick your poison, what the intra area.
We actually are going to cover on that specific. So the question was about, when you have to choose what area to put in, or what link, or what area to assign to a link. We're going to specifically cover that shortly, and it's a little bit more in line. This specific problem is actually in the RFC, so this isn't a Cisco-specific feature. I just want everyone to be aware of how it works. But the general idea is, again, he's right, trying to avoid the intra versus inter-area decision-making. That's basically what this does. So if we turn that off, no capability transit, We'll give it a second. When we run our border routers command, we're going to see that that entry is gone. We're also going to see that R11 is going to start being a little less smart. Oops. We're going to see that it's going to start being a little less smart. And now it's going to prefer the path through R19. And if you look at the way the diagram is built, that would be the path that the virtual link has chosen. You can tell by the cost. So if we send traffic now from R9, yeah, it's one hop shorter, but it's probably a lot slower since we're going over slower links. I just want everyone to understand and appreciate what capability transit is and how it can help you. Now, it's on by default, and you really don't need to think about it a whole lot unless you're in a really complicated troubleshooting environment. Earlier this afternoon, I posted a link that one of my friends wrote a blog on it where he's probably spent like a week on that thing, and I'm not going to go into it too much here, where he talks about the problems that can occur when you turn it off. So leaving it on, that's why it was added to the RFC in OSPF version 2, is because it can cause issues if you don't have it on. So I'm going to turn it back on just so it doesn't cause problems for us later. And then we're going to go back to the slides and review. Okay, so we tested some flows. The trace route shows the path kind of makes like a C around the left side of the network. When we look at the route, we see that R1 is preferring R10 to send that traffic as opposed to following the path of the virtual link. And that's due to the capability transit. And when we looked at our border routers, it revealed that transit capability. Now, the thing that's interesting is that this isn't actually signaled in any of the LSAs. It's not like an announcement. Like you dig in, if you Wireshark all the packets, you're not going to see it. It's a local decision made by R11, but it can be guaranteed to be loop-free because it has insight into both areas and it knows where the shorter path exists. So long as it's receiving that information across the virtual link, it doesn't necessarily have to take that path. Very loosely analogous to like an IBGP type session where I don't necessarily have to follow that path. So when I disable it, of course, we saw the traffic kind of make a curve to the right side of the network. And what I really want to get to is this last part. So 90% of the time, you'll want to leave this enabled, and you don't want to mess with it. But what you do want to keep in mind is that if you end up with the feature enabled, sometimes you can end up with asymmetric routing. So if you look at your topology and you look at R4, I didn't show it, but the return traffic, I guess I could show it here in a minute, but the return traffic is actually going to take the slow path, the upstream traffic, because R4 only has one path into area 1 in the first place. So yes, we ended up with asymmetric routing, but we're guaranteed not to have a routing loop. If we turn it off, we're probably going to achieve symmetric routing in most cases. So if R19 were like a stateful firewall, we might want to disable this feature to make sure traffic goes through it, even if the links are slow. Now, we all agree this is a pretty weird design in the first place. But does everyone understand why you might want to disable it for those specific cases where maybe you need to make traffic go a certain way? Now, we all know how hard it can be to engineer traffic flows with OSPF. We're not given a whole lot of options. This is one option you should consider, but be very careful with it. Optimal routing. So this is going to address the question about how do you choose area assignments for different links. I am behind on time, it looks like. That's okay. So what I wanted, you know what, that was wrong. What am I doing? I'm paying it. So here's what we're getting at. So if you look at the top left of the network, assuming R12 and R1 are, that link is broken between them. Suppose that R1 has some VLANs off it. Some of them are area 0 and some are area 3. And you're asked to decide what link should you put what area should you put R14 to R1 in? So if you pick area 0, then if that link fails from R1 to R12, if you have a source and destination in area 3, you end up with this figure 8 pattern because R14 has to choose the intra-area route through R13. If you choose area 0, or if you choose area 3, then you end up with kind of the opposite problem, where if you're trying to reach an area 0 resource hanging off R1, you take a long path on the other side. So this is that pick your poison comment. So there's a few solutions to it. I'll cover at a high level. One of them is just using like VLAN subinterfaces or frame relay DELCs or whatever other layer 2 encapsulation or virtualization technology that's available. Not that fun. Virtual link, pretty disgusting, but you can do it. if you really wanted to create an area 0 link across it as well. And then probably even worse is a GRE-based tunneling solution, which would work over any transport and would also work over layer 3 boundaries. All of these solutions are pretty bad. A new-ish answer, which is probably like 6 or 8 years old right now, is that you can enable multiple areas on the same link in OSPF. And it's called multi-area adjacency. So we can put it in both. That's why I've got these overlapping colors. So if that link fails, we can access both at the same time. So let me quickly run through this demo just to show you what that looks like. And again, I don't want to harp on some of these easier topics. So if we just look at R12's neighbors, again, the link to R1 is down and broken. And there are 2 destinations. That first one that I just typed out is R1's loopback in area 0. And that second one is another loopback on R1 that's in area 3. You can see one is inter-area and one is intra-area. And if I trace route to each one, you're going to see clearly what the suboptimal routing is in the bottom one, where I have to go make that figure 8 pattern to reach that other area 3 resource, when it would be better if R14 could just forward it straight down. So in order to fix that problem, the command that we use is, let's see, what interface is it? I can just look at my diagram. IP OSPF multi-area and then the number. It's really easy. So I can turn it on here and I can turn it on up here. We're going to see a new neighbor form. And if we check our graph, if we look at our database in area 0, we have that third one down. I have a link to our, let's see, link to another router. Which router? Oh, sorry, I was looking at R1. Let's try this another way. I want to make this a little easier. So I'm on R14. I'm looking at my local LSA1, and I've got a point-to-point connection to R1 inside area 0. That's what we always had. Now, if I run this exact same command and just change the 0 to the 3, now I'm looking at area 3's perspective. I also have a connection to R1. So I have a connection in both areas at the same time, which helps me overcome that issue. And again, we want to test it. So let's trace route to both our destinations, and now they both take the same path. And that's what we want. This is a handy technique, and you can have more than just 2. I just demonstrated 2 here. But this is an interesting technique that I would suggest you do. So this is less about troubleshooting OSPF as a protocol and more about troubleshooting an OSPF design, navigating a bad design, fixing it. Here's the graph. Again, if that link were back up, I draw some dotted lines just to show that connection within area 3. If you want to do this on your own, check your work. Now we're going to talk about hub-spoke stuff. I like this topic because I think a lot of people have this preconception that OSPF doesn't scale over hub-spoke networks. And that's generally true, but there's some ways to make it work pretty gracefully without doing a whole lot of foolishness. So we're going to do this over a DMVPN network. This isn't a DMVPN class, and I'm not going to dig into the details of how it works. For those not familiar, the long story short is that I have a hub-spoke control plane and a GRE encapsulated hub-spoke network, and I can do dynamic point-to-point tunnels between my spokes. That's like the one-sentence summary. So I'm running OSPF over this network. Scalability is generally poor because all the spokes have all the information for all the other spokes. We don't really want that. How can we fix it? Well, I am going to say, if we look at R3, you know what, I don't want to do this. I'm like trying to talk about fun stuff with PowerPoint. I just like, it hurts my head. So much more comfortable here. Okay, so show IP OSPF 1, 2, database, router, self-originate. Remember, what this command is doing is I'm in process 1, area 2. I want to look from router 3's perspective, my local LSA1. We have 2 point-to-point links, 1 to 15 and 1 to 16, over the tunnel. I also have a stub network representing my local interface, my local tunnel interface. This is what happens when you use the point-to-multipoint network type. It's just a collection of point-to-point links. When I say a collection of point-to-point links, it's not like a broadcast network. It's me with individual point-to-point links to every remote item, and then they can each have their own independent costs, just like a regular point-to-point link. It just happens to be on one interface. So from R3's perspective, let's draw the rest of this out. Let's draw 15. So 3 is connected down to 15. We discovered it. 15's got a couple stub networks. It's got another connection up to R3, as we would expect, and that's about it. So it's got a couple stub networks. Nothing too exciting. If If we look at R16, we're going to see the same output. Effectively, all we did was draw kind of like a V shape. We got R3 connections to R15 and R16. R15 and R16 have some stub networks, and that's it. So that's not particularly interesting. If we look at our show IP route OSPF, we've got some OSPF, well, we got lots of OSPF routes, but if I check my routes for 15 and 16 loopbacks, they're intra-area, nothing crazy. The question though, if I were running 100 routers here, we would expect that all those spokes would need to have information for all the other spokes because they're all in the same area. So earlier I made the claim that you can log into any router in area X and draw all of area X. And we've seen that like 5 times today. But is it true in this case? So let's go down to R15 and start the process and see. So show IP OSPF 1.2 database router self-originate. So now from R15's perspective, I want to see, is it the same? So this is exactly the same as what R3 saw. So we're kind of like repeating the same exercise from a different point in the network, which is something we don't always have to do. In most cases we don't, because we're just going to, we're all looking at the same thing just from different perspectives, but because it's link state, we all share that information. So, okay, nothing's really different here. Somebody tell me the next thing I should do. Well, if we only look at this output, what new router have we discovered? We've got a point-to-point link. Who's it to? Yeah, router 3, right? So we're on R15. We don't know about R16 yet. We haven't seen it here, right? So we're starting our discovery process. We don't know that it's there. So let's see what's going on with R3. Bummer. So how does this even work? So if I have a connection to R3 and I don't even have a router LSA for it, what is that really saying? So if I say show IP OSPF 1.0 database, not area 0, area 2, that's all I got. I only see myself. I see no one else. That probably means I don't have any OSPF routes either. Nope. So you might think this is a completely broken and worthless design. But let me ask you this. The advantage is that as I add more spokes, this guy's state never increases. That makes sense? If I can't learn anything from the top side, then you can have however many spokes. This is how we do with our EdgeRP designs and our BGP designs. We do that hub level aggregation kind of thing, so we don't have to share all that state. This is one technique for doing it in OSPF. But how does routing work though? Show IP route. Let's say, how do I get to R3? I just use a static route, a really generic one, and I point it up to the hub. Think about it. If you're in a hub spoke network, where else are you going to send your traffic? I could just have one static route that covers my entire network, or I could have 10,000 individual subnets with all having the same next hop. What's the value in that? This is the logical equivalent of using like EdgeRP or BGP and pushing down that summary route that you all probably learned about in like, for those who ever deployed IWAN or other large DMVPN designs. I see some people head nod their heads, you understand. This is that same idea. Now you might be thinking, oh, if I have the static route, then what about my spoke-to-spoke traffic between the two spokes? Well, that's still going to work because you're still going to have all the DMVPN magic behind the scenes to do the redirects and all that. Again, this isn't a DMVPN class, so I'm not going to get into it. The real point is I want you to understand, and we're going to look at how this is configured here in a minute, is that if I try to do something like trace route to 16, the traffic is going to go through the hub in the beginning. So we're going to hairpin up to router 3, and then we're going to go down to 16. We do it again, it goes direct. So this is a very powerful design. It works just like EdgeRP or BGP in a hub spoke environment. Has anyone been forced through policy or politics to use OSPF over a DMVPN network? Really, only one? Yeah, I know you, but yeah, so I've done this a lot, and I've actually deployed this at scale on like 5 continents, and it works pretty well. Now, to build in failover, I put in the chat a white paper that I wrote last year, and it's free. And if you want to read through that, I explain in detail how this gets set up, how you can do failover, how you can have multiple hubs. It's kind of a complex Anycast design that's beyond the scope of this class. Some of you can probably visualize what that might look like. But I just wanted to show that if you get stuck using OSPF over hub spoke for whatever reason, this is a technique you can use to help scale it. And for the configuration, again, I'm not a big like config looker guy, and I don't even remember what my tunnel was, so It's probably like tunnel 3. Yeah, I'm not that creative. It's just that OSPF database filter all out. So when I first learned about this command like 5 years ago, I was like, this is the dumbest thing ever. Like this is like somebody put this in, they put this in the CCIE lab just to like bother people. But that was just me not understanding. And a few years ago, I was able to learn and really appreciate what this does and why it's useful. It can reduce the state in the network. It's very handy. So let's get back to the slides. Okay, so again, we saw on R3, we had routes for 15 and 16. Here is what our graph looked like from 3's perspective. Now again, you'll have to be careful because when we looked at all of our other designs, we weren't doing any of that LSA1 filtering. So no matter where we were in the area, we could draw the whole network. Now in this case though, when we went to R15 and R16, it didn't quite work and a little bit fishy. So when we look at the way the graphs were built, R15 and R16 are just basically by themselves. They see their own stub networks. They have a point-to-point link to R3, but then when we try to look at R3, it's just there's no entry for it. Remember we saw that? So you end up with this weird disconnected graph that isn't consistent. But the network still worked, and it worked better than if we had not done it. So now the network scales. The amount of routes on that node, on those 15 and 16, is just one static route. I can reach all my remote destinations with spoke-to-spoke resolution. And every time I have like a spoke that flaps or joins the network, I don't have to flood information over the WAN too. So you get a whole lot of advantages. Again, you can make it look and feel like a distance vector protocol, even in this case. Any questions on that? And again, there's a whole white paper that details it. And for those interested, I'd recommend you check that out. Okay. So this is just a little more showing the, the trace route and how it works. I don't need to explain that looking at the routes. I think you all get the point. Okay, forward address. Who knows what this is and who's comfortable working with it? Yeah, like 2 people. So the forward address is one of those topics in OSPF that I think a lot of people are just not comfortable with because they either don't see it a lot or it's kind of like a behind the scenes thing that people are just not comfortable using. So what we're going to do is we're going to do some relatively complex exercises, and we're going to go through, and I'm going to ask you a series of questions, and we're going to answer them as we go through and try to make sense of how this works. So rather than me just like describing what it is, we're going to look at how it works in the network. Because, I mean, for me to sit up here and lecture you about something that you don't already know about is just like a waste of everyone's time. So let's go on R3. And actually, we'll start off down on 15 and 16. So just a quick summary here. If you look at your diagrams, 15 and 16 have BGP peers to R17. Okay, so I'm learning routes from BGP. In this case, I just have one specific route, which is 17's loopback. So we're going to be using this quite a bit. What I've done, what I've configured is R15 is doing redistribution of this BGP route into OSPF. R16 is not. So you may have a hypothesis that if R15 is the only device doing the redistribution, that traffic that flows down the DMVPN tunnel towards R17 would have to forward through R15. That's a very reasonable and logical hypothesis. Let's see if that's actually true. So let's go to R3, and let's say show IP route for 17. Okay, it's an external route. That's cool. And we see the next hop there. So this right here, does everyone know the difference between these 2 numbers, these 2 IPs? So the first one is the next hop. The second one is the originator. So R15 originated the LSA type 5, the external route, and flooded it within the OSPF domain. But the next hop is R16. Why is that? Yeah, they share a network, yeah, but yeah, the forward address, right, that's part of the reason. But why wouldn't it pick 15? Why did it choose 16? Does anyone have a guess? We're going to figure this out here in a minute, but does anyone looking at your topology have a guess? Now, think back to earlier in the class, our first problem, what the issue was there. What do you think the problem is here? Could it be related to that? Maybe a cost issue? So yeah, so what do you think the cost issue is? Is it greater or less than 10? You didn't sound that confident. Greater, is it greater or less than 10? It's greater. Let's see if that's actually true. How can we figure it out? How about we do our show IP OSPF 1, 2, database, router, whatever. Now we blazed past this earlier. Some of you may have noticed this 20. You probably didn't because I was trying to hide it. I was trying to go fast on purpose. But this 20 is the configuration. So you could make a 20 on your diagram if you want, but I did this so that 16 would be preferred. So on that shared network that is going to that BGP, I've enabled OSPF on it, which is weird. Like I get that that's weird, but I'm just trying to demonstrate how it works. If I look at 16, we'll see that the cost is just 10. So it's lower. Now, how would we, if we didn't understand that, what's another way we could look at it? Well, if we dig into the OSPF database for the external route, we can see that. Now, keep in mind, what's different about this command is that external routes aren't specific to areas, right? They're domain-wide. You can't filter them at ABRs and things like that. Forget about stub areas for now. So I'm not specifying an area here because it doesn't really make sense. But if we dig into the details of it, second from the bottom, we have this thing called a forward address. What is that? What do we think that is? Now, actually, it's probably not fair to ask because you wouldn't know. That's the IP address on R17. So that's R17's IP. And let's see if we do a show IP route for it. We're going to see that it's just going to be that /24. So that's that shared subnet between 15, 16, and 17. And you can see I'm learning it from R16 because that's the lower cost path. So the way I like to think about the forward address is it's another shortcut technique. So we learned about transit area earlier, and now we're seeing another shortcut technique when it comes to redistribution that says, maybe I've got these two guys are doing, one of them is doing redistribution, but he's closer to the destination. So maybe my final destination is somewhere on this side of the room, but my good friend Travis here is doing the redistribution and feeding it to me. But if the forward address is through Mike and the destination's on this side of the network, it makes sense for me to go this way rather than that way. Does that kind of make sense? That's what we're dealing with here. If it's hard to visualize, just imagine that there were maybe 5 or 6 other routers between R15 and R17, but R16 was much closer, so we want to take that path. So maybe we have, if we had, let's say, instead of just 2 routers there, let's say we had 10 or 100. And that sounds ridiculous, but I've seen it. I've seen that in some networks. Do I really need all 100 to do redistribution? What if I just do 2 for redundancy, maybe 4? So now I only have 4 copies of all the LSA 5s instead of 100, but I can still use all 100 forwarding paths based on the location in the network. So it can be a pretty handy technique. Let's go and just quickly review that. So if I do the show IP route, which I didn't show in the demo, we would see that R15 is doing the redistribution, but R16 isn't. Maybe we form a hypothesis that 16 would never be used for forwarding. Clearly, we proved that wrong using a combination of our show commands and our trace route. The LSA5 was originated by 15, but we took a path through R16 due to the forward address, kind of like hinting at a better path. Now, to find the shortest path to the forward address, when we looked at those details, you see those bottom 2 squares. One of them had the metric of 20, one had the metric of 10, and we were able to sort out why it took that shorter path. And that's the technique we used for it. What happens if we go outside of our local area? So we were on R3 before, and we were like, okay, I want to get to R17. But now I'm in a different area. I'm in area 0, and that individual wants to get to R17. These are 3 key questions. When you're dealing with external routes in OSPF, and you have a multi-area network, you need to know how to answer these 3 questions with complete clarity. Because if you can't, you're going to be hurting real bad when things break, because it's going to be very hard to troubleshoot. So the first question is, where did metric 1 come from? So you know what? I'm going to open the demo now so you can see a little better. We're going to go on to R2, which is in area 0, show IP route for 17. So I have this metric 1, then I have forward metric 30, then I have this from R15. And remember, R2 is not in area 2. Therefore, it does not have access to R15. Remember we drew that big area 0 graph earlier? It's not there. So who wants to take a guess at where metric 1 came from? Like, if I'm digging in the database, where did it come from? No, it's not the metric to the ASBR. That's something else. That's a great guess, though. Where did metric 1 come from? Right. It's the default seed metric when you redistribute from BGP into OSPF. And I'm not going to get into like the table that shows all the values, but let's see if we can prove it. So if we're claiming that it's the default seed metric that comes at redistribution, it should be carried within the LSA5. It has nothing to do with the topology. We could be right next to the ASBR or 100 miles away, and that number would always be 1 because I'm using type 2 externals. The reason I'm using type 2 in this demo is because I think it's a lot more interesting for what I'm going to show you, because when you combine the metrics together with type 1, it's just not as fun. I mean, who flew out here to San Diego to not have fun, right? So let's take a look at that. If we look at the external, not router. Look at the external there, third from the bottom, metric 1. So that was originated at the point of redistribution, and of course you can adjust it. That metric 1, that's where it came from. Now at the top, the very top line at the screen, it says forward metric 30. What's that? What's that?
The cost to get to the subnet through the links.
So the cost of the forward address.
Correct.
That's right. It's the cost of the forward address. How can I show that? What's a couple ways I could show that number? What if I just do this? Is that one way? Metric 30? Okay, so that's a good starting point to say, yeah, the cost of the forward address. That's a good, like, quick, like, punch them in the stomach answer. Now, like, what's the rest of it? How do we come up with 30? Like, yeah, you can look at your diagram and you can count 3 black lines. What are the 2 components that make up this number? I'll give you a hint. I'll highlight it. What 2 components make up that number 30? Think back to just basic inter-area OSPF. There's no tricks here. Okay, there's a cost to the border router, and then what? That's right. So how can I get those 2 numbers? Okay, I mean, yeah, but so the easy answer is, if I can take a little bit of a shortcut here, and I can say, within area 0, what is my cost between router 2 and router 3? Now, they just happen to be right next to each other, but if it were farther away, this would save us all that time, would it not? Cost of 10. How do we get the other 20? That's probably the cost from R3 to the subnet, right? How do we get that from R2? Because it's not in area 0, so we can't just we can't look at our type 1s or type 2s. What do we need to look at now? No, that's a type 1. What do we need to look at? No? Come on, guys. You're like, every number except the right one. 3. It's the summary LSA, right? This is an inter-area route. It's described by a summary LSA originated by the ABR to describe destinations in a different area. That's all this is. There's nothing external about this route. It's just a regular subnet in a different area, right? Don't be fooled. Don't get too caught up in the external context. So I can say show IP OSPF 1.0 database summary. So I'm looking at my LSA3s. I'm looking for the 10.0.15.0, and it should have been advertised by router 3. How's that for a show command? This is being surgical and specifically looking for the information that you need. So in this case, I know it was coming from R3 because that's the only ABR into area 2. R3 is saying my cost to the final destination, or my cost to that subnet, is 20. 20 plus 10 is 30. That's how we came up with that number. This is just basic inter-area OSPF stuff. And I'm not saying basic to be insulting. I'm saying basic because this is how it works behind the scenes. And you'll want to understand this when you're going through and trying to figure out where those numbers come from. I'm of the opinion if you use a show command and it gives you a bunch of output, you should be able to explain where that output came from. If you say, okay, this 1 means this, that 30 means that, and blah, 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 okay? So let's go back. So we answered our first 2 questions. How do we answer our last question? The last question was, yeah, I almost forgot it too. So the last question was, where did this R15 come from? So if we do our show IP OSPF 1.0 database router for 15, there's obviously not going to be an entry there, and it would help if I didn't type 10, if I typed 1.0. But there's not an entry there because R15 is not in area 0. What's up? Why? How do I get past, how do I overcome this? How does OSPF overcome the event of performing an inter-area lookup on an external route? What LSA is used here? I heard 5, that's not correct. 4. The type 4 LSA is probably the most poorly understood LSA in OSPF. All it does is it represents an ASBR in a different area. Because if we're going to do our graph lookups and we're going to try to build a topology to somebody who originated a node in a different area, I need to be able to do my lookup and know where that node is, and I need to know the ABR by which I can reach that ASBR. So, show IP OSPF 1.0 database ASBR summary. OSPF v3 that is used for IPv6, they've changed the names of these LSAs for the better. They call this an inter-area router, which to me makes a lot more sense than this, but that's what it's called in v2, the ASBR summary. So the specific router I'm looking for is 15, and it should have been originated by the ABR, which was R3. The metric is irrelevant right now, so don't get focused on that. But this just gives us access to know that R15 exists in the network. So it was originated by R3, and the ASBR router address is the .15. This is the answer to our third question. So we answered all 3. Metric 1 came from the seed metric at the point of redistribution. Forward metric 30 came from the cost to the forward address subnet, which was a combination of the cost of 10 inside of area 0 from 2 to 3, and the cost of 20 from router 3 down to the subnet. And we discovered all that, again, from one router. We didn't leave R2 for any of that, did we? That's what you need to keep in mind, is that we're not jumping around the whole network. We can focus and know exactly what we're looking for, and taking advantage of the fact that OSPF is link state, and every router has a similar view of the network, unless we're doing some filtering that we saw earlier. So we answered where metric 1 came from. We answered where 30 came from. Again, this is the superficial answer. This is like the quick, you're taking a test, and this is the answer. But if you really want to understand it in detail, you need to combine the cost to the ABR plus the ABR's cost into the area. This is just basic multi-area OSPF stuff. Combine the cost to the ABR plus the summary LSA cost. Where did R15 come from? It was learned through the LSA4, the ASBR summary, or the inter-area router, depending on how you want to look at it. Some people call it like a glue LSA. I think that's just even more confusing, so I don't prefer to call it that. The one thing, if you don't remember anything else, used when performing an inter-area lookup on an external route. Somebody described it to me that way. I wish I remember who. I'd give them attribution, but I heard that and it stuck with me, and that's how I always remember it. It's a very useful thing to keep in mind. Clearly that was way too easy, so let's make it harder again. I realize that wasn't easy, I'm joking. It's difficult, but we're going to make it harder anyway. So what happens if we go even further away? Don't let it psych you out. It's not any harder. Okay? It's the same process. Think about our 3 questions again. Now, when I go on here, our numbers are going to be different, but the process is going to be the same. Should be R13. Show IP route for 17. So I've got metric 1, forward metric 40, and from router 15. So where did metric 1 come from? Yeah, it hasn't changed, right? Show IP OSPF 1 database external, blah, blah, blah. There. Easy, 1, third line from the bottom. Where did metric 40 come from? Give me the easy answer first. Where did it come from? The cost of what? The cost of the subnet. Not the router specifically, but the cost of the forward address. The forward metric is the cost of the forward address. That's why they call it the forward metric. So if I do this, see the subnet there is 15.0/24. The metric is 40. Where did the components of 40 come from? I want to break this in half. Look at the topology and tell me, what do you think? What 2 components make up this inter-area path? Cost of the ABR, and we have 2 of them now. It's the ABR's cost to the subnet, not the ASBR. Right, so we need to identify what is my cost to the ABR, and then the ABR's cost to the final destination. So let's go through that process again. Show IP, OSPF, border routers. Let's look at our two ABRs. Uh-oh, we have two now. Which one do I pick? A lot of people will be like, oh, it's a load share. No, it's not. You only did half the work. You got to be careful not to fall in the trap. When you look at something like this, you might be like, oh yeah, he's just going to do load sharing, and it doesn't. No, you didn't reconcile the other half of it. What we also need to look at is the summary LSA for that destination. And then we have two entries here. We have one that was advertising router from R1 and one that came from R14. Should be obvious which one we choose. Now, the reason I say obvious is we have 10 plus 30 versus 10 plus 40. Okay, so I'm going to choose that one. As a quick aside, if I wanted to make this load share, what's one quick change I could do on R13? What could I do? Increase what cost to what? Increase the cost to R1, make it, what should I make it? It's 10 right now. That's right. Now this is where, again, you need to just kind of think about how this works though. See that? So now we get this load sharing. I mean, I get we didn't change costs on both sides, or I'm just trying to demonstrate, but when we look at our border routers, you see now we have this cost, 20 and 10 down at the bottom there. So now when we look at this, you might be saying, oh, 14 is the better cost. Well, now we're dealing with 20 plus 30 versus 10 plus 40. They're both the same. Okay, so you just want to keep in mind that, I might be close to this ABR, and that ABR is far, but this ABR may be closer to the final destination. So that's why you need to reconcile both, and you don't want to jump to conclusions. I'm going to change that back. Okay, so we answered our first couple questions. What about our last question? Where did 15 come from? Came from the LSA Type 4, originated by the two ABRs. Now, in this case, it doesn't really matter which one gets chosen because we don't really care about the metric, but I just want to demonstrate how we even know about it. Show IP, OSPF, 1, 3, database, router. This is going to fail, of course, because we're not in the same area as the ASBR. But if we just change this to, say, ASBR summary, we're going to see two different entries. So both ABRs are telling me about the path to reach R15. All right. For those of you who have never done this before, is this starting to make sense? Are you able to kind of high level follow what's going on here? Good, good. That's the point. There's no expectation you're going to be out of here and like, yeah, show IP OSPF database all day. Like, that's not going to happen tomorrow. I mean, if you think I have been doing this for a long time, that's the only reason I'm like, yeah, whatever. I don't even need to look one-handed, left-handed, It's different when you're doing it for the first time. So just be patient and be generous to yourself when you're first learning it. So I don't know that I need to go over all these slides over again. Again, focus on this part. We looked at an example of where we had mismatched cost and we were able to do all these funky things. Just keep in mind that if you're only looking at the costs on half the network, you're going to get the wrong answer. Always, again, this is just basic inter-area OSPF stuff. Don't let the external and all the other stuff fool you. If you have an inter-area OSPF route, you just have to know how to compute the cost. And of course, the border routers command, I've been using it a lot today. You don't have to use it because the answers are in the database. Border routers just summarizes that for you and gives you that information in a clean format. Let's look at some problems with the forward address. So I'll let you all read the slide. I'm going to make a change. I'm going to make the change and then I'll switch it over. So basically what I did, I put this little area filter on R3. And I said, I don't want to advertise this forward address subnet into area 0 or anywhere else. So we can pretty quickly, easily see if that worked or not, and it did. The real question is, are we going to have a route for this external? Is this going to be in the routing table, yes or no? Why? Why should it? Why do you think it should be? So if you don't have a route to the forward address, how do you know where to go? That's the problem here. And you might say, oh, wait a minute. You taught me the database trick, and I can just do this number, and clearly my entry is here, and it's healthy, and there's no problem. But if you have a forward address that's identified, you need to have a route to it, and we don't. This is important to keep in mind. Now, there's a lot of ways to overcome this, and we're going to look at one of those approaches now. But I want you to understand this, because a lot of people get to this point, and they see the LSA, and they feel like they've gone as far as they can, and the route just isn't in the routing table. So they start clearing OSPF, and they start upgrading code, and they start doing all the wrong things. I mean, we laugh. Who's done that? I mean, honestly, who's done that? Who's run into a problem, and they just didn't know? And at the end of the day, you found out that you just lacked the skills. All of us probably have been there at some point. It's just the reality. I'm trying to help make that less common. So we don't have a route to this. If I do something goofy, like just toss one in here, like a static route, and you're laughing because you know it's not going to work, right? I got a route now, but it's not going to solve my problem. You need to have a route that's OSPF learned, and it has to be an internal route. So it has to be intra or inter area, which means it's trustworthy, it's inside OSPF, and it's guaranteed to be loop-free. That's why it has to be that way. So I'm going to delete that dumpy static route, and we're going to try to solve this another way. I don't really need that forward address route, because what if we collectively agree as the design team that, you know what, we're okay with traffic transiting R15. Like, we don't need the optimal path through 16. It's not that important to us. At a high level, what do you think we could do? We could maybe just remove the forward address somehow and just say, stop doing it, and just force all the traffic through R15 instead. Now, this is how redistribution works with OSPF 99% of the time anyway. I had to work hard in order to make it work this way. Most of the time, you wouldn't be running OSPF on your interfaces towards your external peers. The reason I did that is so that by sharing that network, I could get this idea or this performance out of it. There's a few ways that we can turn it off. So we looked at all this. We looked at the problems. We looked at the a valiant attempt, which is my dumpy static route that did absolutely nothing. Now, there are 3 ways that we can disable the forward address. We can completely turn off OSPF on that interface number 3 on 15. We could change it to a point-to-point network type, which would also disable this feature because it only works when the network is a broadcast network type. Or we could make it a passive interface. It seems awkward that there's so many ways to make this not work, and this is typically one of these would be true. Most of the time, you wouldn't have OSPF enabled at all. So we can pick any of these choices. I'm just going to do, I don't know, I'll do network point-to-point. Who cares? And if we make this change, we're going to see a little bit different, little bit different behavior. So I'm going to go down to 15. I'm going to go to interface 3. I'm going to say IP OSPF network point-to-point. And then I'm going to go back to R2. I'm going to not look at I'm going to look here first, and the difference is the forward address has been zeroed out. 99% of the time, this is what you're going to see, okay? So everything we talked about before is those rare cases when you're dealing with a completely messed up network design and you've been asked to troubleshoot it and you don't have a clue what's going on and the diagram's wrong and everyone quit because the job is so terrible. So, yeah, you all know. So you're trying to troubleshoot it, you might just be able to turn it off and have everything work again. Now, the reason here is because if you don't have a forward address, the behavior is that traffic will forward through the ASPR. But let's go through our questions again, just as a final review. You know what? Let's make it harder. Let's do it from R13. That's too easy. I don't like easy. So we'll do it from R13. I've got metric 1, I've got forward metric 30, and I've got this R15 again. So this is like the 3rd or 4th time we're seeing this. Where did metric 1 come from? Came from the seed metric. So show IP OSPF1 database external for 17. There it is. Where did forward metric 30 come from? It's different this time. So it's not the cost of the forward address anymore because there isn't one. Instead, it's the cost to the ABR itself. So it's the cost to R15, not to a subnet, but to a node. So how can we find that? We can look at our database. There's a few different ways we can do it. I'll show you the long way first. We can look at our ASBR summary for it. And we have two choices here. We have metric 20 and metric 30. This is R1 and R14's costs to get down to R15. What are we missing? So we're standing on R13, and we just talked to the ABRs. We said, hey, what's your cost to get to 15? What's your cost to get to 15? What other piece do we need? We need our cost to get to the ABRs, right? Show IP, OSPF, border routers, include ABR, 10 each. So basically, I'm comparing 30 versus 40 here. 30 is less. That's the number we choose. There's an easier way. What if I just looked at my border routers for 15 from the beginning? You can also get it this way because the border routers command is smart, and it just doesn't tell you about ABRs. It also tells you about ASBRs in the network. So this tells you in one go the path, the cost to get to that router. Now, of course, we saw it from the routing table as well, but I just want you to be aware that behind the scenes, looking in the database, seeing the 20 and the 30, and then doing the 10 and adding them and doing all that, that's it right there. This is the shortcut. Here's another way that you can see the cost from R13 down to R15. These are handy techniques for troubleshooting so you can answer the question on where these numbers came from to make sure that they're the numbers you expected. And of course, if we just want to get creative and send traffic, second to last hop is R15 now. And I get that I didn't do a trace route earlier when it was 16, but we did it from R3, so you can kind of get the idea there. Let's go back to the slides and do a quick wrap up on this before we move into our final set of topics. So we disabled the FA. It got set to 0 because we turned off the OSPF on that interface, or we made it a point-to-point network. And then we use our border routers command combined. We use the border routers command to get the shortcut, but to do it the hard way, we did our 2 steps. Just like for inter-area, we had 2 steps. We looked at our cost to the ABR, and then the ABR's cost to the final subnet. In this case, we're not dealing with inter-area anymore because the forward address was filtered. We're saying, what is my cost to a remote ASBR in a different area? It's my cost to the ABR, and then the ABR's cost to the remote ASBR using the type 4. This takes time. It's going to take time to go over multiple times and get comfortable and just recite this to yourself and become comfortable working with these technologies, especially if this is something you don't do all the time. Oftentimes we take show IP route for granted because it gives us so much information at so little effort, and that's useful. But when you dig into how those things work and you see numbers you don't understand, it starts to become really important to see how it works behind the scenes. Now we're going to talk about NSSA a little bit, but not really. What do I mean by that? Last year, I talked about this for some time. Actually, I'm going to skip that slide. We'll talk about this first. I had another idea. I don't believe in doing the same sessions year after year with the exact same content. That's boring. Boring for me, it's boring for you. So I had 2 hypotheses. One, that people don't want to see the same stuff over and over. You could just watch a recording. And 2, last year I wrote an automation tool to assist with troubleshooting OSPF. So you can integrate this in your processes. And I'm going to do a very brief demonstration of that tool, which is published through DevNet. It's open source, and we'll talk about it later. And again, the votes are pretty clear. Most people wanted to see that. So that's what we're going to talk about. I'm just going to go back a slide here. This is what the graph looks like in the network. It's basically 4 routers in a line. If you think about it, the routers on the left are ABRs. We're not really going to do a lot of NSSA stuff in this class. I used to do it. I decided to pull it out so we could do something different this time. All the material is in the backup, though. So if you did want to talk about that more, you can. What I've done is I've added a new subnet there. I put Ansible. Who's ever heard of Ansible? Leave your hands up if you've used it. Okay, so maybe 20, 30. So I'm using this tool to log into the devices in the network and make sure that there's no problems. Now that's a tall order because how do you know what's a problem? Like you need to define what success looks like, and there's a lot behind the scenes. I'm going to show you a little bit about how that works. So the why, this is probably pretty obvious. I thought about not even having this slide because I don't think there's any real controversy here, but when you use automated troubleshooting, you log into a router, you do show commands. Show commands typically don't crash routers, not very often. So there's not a whole lot of risk in deploying this. You're not trying to do configs, nothing that would cause an outage or require a maintenance window. Obviously, it's going to save you time. The tool I'm going to run is going to check these 4 NSSA routers and do a pretty detailed analysis of their everything from their configuration to the health of the database to a whole bunch of different nerd knobs and counters that would take probably 6 months to talk about in detail. It'll run in like a minute. So it'll save you that time. It'll also collect all that output in a log, so even at a minimum, if something's broken, you have all the output at your disposal, and you don't have to go rooting around every device. You define what success looks like. If you want the test to be very strict and fail every time a router sneezes, you can do that. If you want it to only fail when there are major issues, you can do that too. So I'm going to talk a little bit about how this works coming up. Here's the high-level architecture. So on the right, the way Ansible works is we have a playbook. A playbook is a collection of plays. So who likes American football? I say American because, like soccer, right? So I know. In Europe, everyone would be like, what are you talking about? So a playbook. Imagine you're a football coach, you've got your playbook, and on each page you have a play. Every play is going to have some specific players assigned. Like this is an offensive play, this is a defense play, this is a special teams play. Within that play, there's going to be a list of tasks. Quarterback goes this way, running back goes that way, wide receivers go this way, all that. That's the same idea of the way this works. So we have these individual plays and tasks. This is just a task execution framework. We're not going to talk about all the guts of Ansible. I just want you to get a high-level idea of how this works. Then we have a few different classes of variable data. The color might be a little bit dark. I don't know how hard that is to read, but we're going to see this in a second, so don't fret if you can't read it. We have information that is area-specific, like the area ID, the area type. Like if you're in an area, you can't be different types, right? The number of different kinds of routers in the area, things like that. And then we have a router-specific data. How many neighbors do you have? What areas are you in? Should you be in ASBR, yes or no? Those kind of things. So we're kind of declaring the state of the network that we expect to see. So obviously, if we're running this on a DMVPN hub, we might not want to specify the neighbor count because that can be different every 5 minutes, dynamic. But on the spokes, maybe it's always 1 or 2. Maybe that's a fixed number. So you want to be smart about what you check and where based on your design, and you have all that flexibility. There's also process level data, things like do you have global features enabled? What about your statistics and the number of failures and other things? I just couldn't fit it on the slide, but we're going to see that shortly. So the high-level operation is Ansible needs SSH access to our devices, so I've got it hanging off like the server VLAN in my network. It's going to SSH into a router, and then you can see in the blue just the high-level operation. It'll log in, it'll run some show commands, it'll parse the output, and then it'll go and do a bunch of detailed checks. So for example, let's make sure that R6 doesn't have more than 1,000 Type 7 LSAs, which are NSSA external. So maybe you're doing redistribution from BGP, and you don't want to redistribute the whole BGP table. So you can tell Ansible to say, make sure that there's not more than this number, and if there is, then throw a flag, because we want to know about that. Maybe it doesn't cause the network to melt down right away, but it's still a misconfiguration we want to get in front of, so we want to be proactive. We can also check other things. There's a whole lot of things that get checked. I'm not going to go through all of them, but this is the high-level operation. So I'm super creative with my naming, so I called it NOTS, so Nix OSPF Troubleshooter, haha. So let's take a look at how it works. Okay, cool, so the date's correct. So this is just a Linux box, got Ansible installed. And what we're going to do is we are going to run this, but I want to show you some of the files first. So first, we're going to look at the group variables for the process level. So again, I'm not going to get into the Ansible-ness of it, so if you have specific questions about it, let's talk after. But if you just look at this at a high level, you can probably understand. The process ID on these routers should be 1. The max LSA5s in the network should be 200. Notice that the max LSA5 option isn't area or host specific, because LSA5s are a global setting, are they not? You can't really filter those out. Now, obviously, if you're in a stub area, the script is smart enough not to check for LSA5s there. In fact, LSA5 should be 0 in a stub area, should it not? So all these things that we know about OSPF can be checked automatically, and you don't really require a lot of user input. All those other numbers, like the SPF numbers, for example, those are the default values on the newer versions of code, and generally speaking, you don't have to, but in most deployments, you'd have these numbers consistent in your whole network, and we want to make sure that they are consistent. Because if they're not consistent, you could have issues or performance problems. So this asserts that they're consistent. And if you don't want to check it, delete those 4 lines, and it won't be checked. So this is a very strict example of where I'm checking a lot of things, because I want to demonstrate everything it can do. So let me just demonstrate all these other numbers. I don't know how much people use these other commands. I'm just going to show an example. I'm looking at this was the show IP OSPF traffic command. You see down there it says OSPF header errors and OSPF LSA errors. I collect all that information and I check to make sure that they're all 0. So clearly we can see that that one has unknown neighbor 3. That happened because R11 was doing virtual link stuff and we were changing the state of the virtual link. So there was a point in time when R11 was not able to form a virtual link, but R4 was. You remember we were in that kind of transitory state. So if I run this tool, we should actually see, well, actually, you know what? R11 isn't actually being tested. I'm only testing the NSSA routers just to keep it simple, but if I were running this on R4, that would actually be an issue. Either way, what I'm getting at is that those thresholds that I've shown were the upper bounds for the number of problems that we could have. So for example, if you want to make sure that all those numbers are 0, you can just do something like this. If you want to be a little more forgiving, you could say, I'm willing to have a few errors, because a few errors usually means, okay, we were doing a password rollover and a couple hellos had a mismatch, but it wasn't a big deal. If the numbers are in the millions, it's probably been broken for a long time, right? So maybe you want to be a little more generous and increase them. But by default, I leave them at 0. So those are the process level parameters. We can look at the group level parameters too, which would be in the OSPF routers group. Again, don't worry about all these file names. It's all documented. I just want to show you kind of high level. So at the top, that's just login information. Cisco is the username. Don't worry too much about that. Focus on line 14 and below. Here's where I define my areas. I've got area 0, which is a standard area, has to be. How many routers are in area 0? 9, right? There were 6 in the middle and 3 at the top. I want to make sure that there are exactly 9 routers in area 0. How many DRs were in area 0? Only 1. It was between routers, I think, 1, 2, and 3. So I want to assert that that's true. How can I do that? By checking the database. Likewise, for area 1 and area 4, we have another standard area, NSSA. I have some different parameters in each. Number of routers, number of DRs, basic settings. Anyone have questions on that? I can set thresholds for maximum LSA3s, which is a per area setting. I can set maximum LSA7s per area setting. Obviously, behind the scenes, like for example, if you're in a standard area, you should never see LSA type 7s. Those are NSSA external, and they never leave the NSSA. Is that correct? So I can make these other checks behind the scenes without the user having to tell me. I can be smart about it. Last, I want to open the host-specific data. So this is where I have the host inventory. I could have put all my hosts in here with their specific data, but I just limited it, excuse me, I limited it to just the NSSA devices. So R4 through R7, if you look at your diagram, this information should be correct. R4 is in 3 areas. It's in area 0, area 1, and area 4, and it should have 5 neighbors. And if you look, the virtual link counts, of course. R5, R6, R7, I'll give everyone just a minute to look at this while I grab some water. Should all be right. And you can see I have an option called should be ASBR true for the devices that are redistributing from EdgeRP. So the combination of all these variables, host-specific, area-specific, process-specific, all of this combines into a very detailed test. So we can run it, and I'm going to put the word time on here, time Ansible playbook, and I'm going to run the thing. So I'm not even going to try to explain because this is it's going to fly by, but what you're going to see is that as it goes through and it collects all the information, this is the slowest part. It has to log in, has to run show commands on all the devices, then it's going to do all the parsing, and now you're going to see a bunch of stuff fly by. So you can see it's checking all these errors on every interface, on every device in every area. Who wants to do that manually? Right. So Yes, I taught you the advanced techniques about drawing the graph and troubleshooting, but this can be a real time saver when you're trying to ensure you look at your diagram and someone's like, oh yeah, Travis, this diagram is right. I'm telling you, I nailed it. I'll take another job. I'm out. Have fun. And then you're like, well, let me make sure. And you can use this to build all that variable data and run the tool and see how accurate the diagram really is. So that can save you some time. Now this will end here shortly, and I put the time on it, so we should see it should take about a minute. You can see everything came back okay. It took about 55 seconds, and you can see right here, the number of tests was different on every router. Why do you think that was? Some routers are in more areas than others. Some routers have more things to check. Some routers have more neighbors, right? So it's smart enough to do the right checking on the right devices based on what you want to do. And all those variables are optional. You don't have to specify any of them. You're like, I don't want to, I don't know how many areas this router's in. All right, don't check it. Or I don't know how many neighbors it has. Or I don't want to check those SPF thresholds because they're not important to me. Fine, delete it. Delete it from the variables and it won't get checked. So we can, now that we got, it's good we got some time. Let's break some. So if I go on to R4, and we could break and see, here's the log. So I turn on logging, by the way, just so you can see this is Ansible logging in and just doing the show commands. You know what? Before I break it, I want to show you one last thing. Automatically in the background, what I did is every time you run the tool, a folder gets made with a date timestamp, so that's today, right now, with a text file for every router in your inventory. And in that text file is the output that we saw from each device. So if we look at R4's output, I made it real easy. I have a little banner up top that says, here's the output from this command, and there's all the output. And we make our way down. Okay, show IP OSPF1, that's over, and now here's the next command. So I consolidate that into one big file. So if something went wrong, or if you didn't want to go and log into 100 devices, it captures it all for you locally. So if the tool didn't catch the error, maybe you've got an error and the tool just didn't find it, because I can't predict the future, you can use this to at least collect the information, and you can see there's just a ton in here. Now, all this stuff gets parsed into the machine and gets checked. But if you want to do a manual verification or a backup or whatever, you have all of it available automatically. Let's go break something and see what happens. So if we go to R4 and show IP OSPF neighbor, I don't even know what interface this is. It doesn't really matter. So if I shut this down, and I look at my neighbors now, we agreed that there's only 4. And if I go back and look at my inventory, row 13 clearly says there should be 5 neighbors, right? We would expect this to fail. So there's a few ways we can do this. We can run the playbook again, and it'll run on all of our devices. R4 is going to fail, and then the rest will continue. The only problem with that is that because there's so much output, it might get lost. So I'm going to do a little bit different approach. I'm going to use this limit option, and I only want to run the tool on a subset of routers. I only want to run it on R4. Now, in real life, you just run it everywhere because you wouldn't care, but I just want to show you what happens when there's a known problem. And I want to show you the error message that comes out of it. And you're going to see, it might take some time, obviously, depending on the sequence of things that get checked. So it checks all the process level errors first. At some point, it's going to check the neighbor count. It's going to say, hey, I expected 5 neighbors because that's what you told me, but I only saw 4. That's basically exactly what it says. And it tells you the code, exactly what failed. Again, we don't have to get into exactly what the code looks like, but the message is clear enough. And then you look at your diagram, like, yeah, there should be 5 neighbors there. And then you can go and fix the problem and rerun it. So, I can go back to R4. I can say, turn this back on, and it'll work. So what questions do you have on this tool? Or anything, really. We're at a point in the class where you can really ask any questions. And I'll put the slides back in a second. Yes?
Do you have any particular Python modules or anything on Ansible to run this?
I made it like 100, I made 115 minutes without coughing, so that's pretty good. You need to, if you install Ansible, it will come with the core module. So let me answer it this way. I did not use anything outside of Ansible core. I did not use any custom modules or anything like that. Everything is self-contained in the tool. If you pip install Ansible, and you're at least on version, I think 2.7 or newer, it will work, period. I mean, those other modules are great, but it's a new dependency, and for people new to Ansible, it's like, oh, now I need to go learn this thing. I try to avoid that when I can, and in this case, I could. So that worked, and I'm going to go back to the slides now, and we're going to finish up. Okay, last topics here. This is important. The graph, this is the core technology of OSPF. No gimmicks, no shortcuts. No, we didn't rely on basic OSPF commands. We looked down and dirty, how does it work? Make the time to draw it. When I say draw it, you remember earlier in the presentation, I had those boxes and the lines and all that. Do that on your own. Get accustomed to doing it. It will change the way you look at OSPF. It'll change the way you troubleshoot. Yeah, physically draw it. Yeah, that's right. Maybe not every single time for every single issue, but get accustomed to doing that. I was able to teach people who were pretty entry-level network guys. We got together. We were on travel together. It was like a Saturday. I spent about 3 hours with them, and they completely mastered this. So if you go home and you're willing to commit an afternoon and just go through some of the exercises that we talked about today, make a topology, use your work topology, and just go and draw it and get accustomed to it. It doesn't take that much practice. Make the time to draw it because it will reveal everything. Empirical evidence. Opinions are important. Hypotheses are important. Prove it. You got to do it. Otherwise, you're just guessing. You're throwing punches in every direction, hoping you connect, and that rarely happens. Here are some links. Again, I posted these in the chat, so you can check all these out. Link to the GitHub configurations, which is one repository. So initial configs, final configs, diagrams, all the stuff if you want to go through this course, as well as the other trouble tickets we didn't have time to go through. The OSPF troubleshooter code, this is published through DevNet. It's the most popular piece of code I've ever written. I suggest you check it out. I think you'll enjoy it. I've used it in production for more than a year now. It's a real time saver. You can extend it. You can do whatever you want with it. You can steal it. You can say you wrote it. I really don't care. Reference content, again, troubleshooting adjacencies and performance. This is the content I didn't cover in the slide deck, but some of that is in the deck. Some of you may remember that some of my people who voted wanted to see these topics, but they were a minority. So I figured a good compromise was I'll add it to the presentation as hidden slides. Those people can do it on their own. Twitter, questions, comments, using the tool, need help with it. It blows up when you run it. Let me know. I can help. The WebEx teams, again, if you want to get on discussion, some of you have been talking on mic all day, and that's great. If you ask questions there, one of us will answer it. The session's open for like another week or so-ish, and I'll be able to address your questions if you have anything specific. That also includes doing the feedback. So through your app, you can do feedback for the session. Feedback is obviously important. I know every speaker says it, but those numbers determine whether we come back or not. They help shape what Cisco Live is. So if you enjoyed this session with the demos and the fun and the scenarios, Cisco needs to know that. And if you thought, if you wanted 2 hours of PowerPoint, like a college lecture, Cisco needs to know that too. So I'm not telling you what to say. Say what you think, and so we can change how Cisco works or do it different ways. All this other stuff, you've seen it a million. I'm not even going to talk about that. What questions do you have? Yes?
If you're going to do this session next year, what are you going to change?
That's a great question.
Twitter poll.
I got to do a Twitter poll. I got to think of something. I haven't thought about that yet. If you have an idea, please let me know. Put it in the chat. Everything's up. Any other questions? We got 30 seconds left. Yes?
OSPF v3, you've seen how much?
I've seen some adoption of OSPF v3, not a ton. I've seen a lot of OSPF v3 with IPv4 as a setup, a precursor to IPv6. Very similar techniques to what we looked at today, obviously different commands and stuff. A couple new LSAs, but adoption is starting to increase. Any other questions? All right.